Abraham ine. It's JOSHABRAHAM ine. And we are back with the daily bio coding. I couldn't do this yesterday cause I had an exam, but today we're back. And oh, we should use this one. Bye. Yeah. Okay, everything's back. Oh, just close this. Okay. Well, whatever. UTTP Sans. Hey yo, what's up? For checking out the stream. And Devoto did. Hi. UTTP Sans, I am very early. Uh for the stream, I guess. Well, I really appreciate you people for checking out the stream. I really appreciate that. Gotta get it to stage manager. And so UTTP Sans. These are new people, if I understand. Oh, it's this guy. I do remember. So UTTP Sans, I really appreciate for checking out the stream, and Devoto did. I really appreciate for checking out the stream. Fuck this. Wait, oh no. Trajectory post processing. This goal is to make the protein appear continuous and centered inside the water box. Okay. Paste that. Well, what the hell? Select one protein as the group to be centered and 0 system for output. We will conduct all our analysis on this corrected, more formally remain trajectory. Okay. So we have to take 2 was 1. Protein is 1. Select a group, selected 0. Clone open commander, let's go! Let's go! Fucking go! I think I should be done within today. At least for the water lysome simulation. But give a short practical plan. Extract commands. You can copy paste to do the common follow-ups. Final frame, energy time. Last written frame 100 time 1000. Wait, what does this say? Root square mean deviation. So according to the okay, root mean square deviation. Let's do the root square mean deviation. Oh, again, I gotta choose 4 backbone for both least square fits and group of RMST calculations. The TU flag will output the results in terms of NS, even though the frames in the trajectory were written in the timestamps in PS. This is done for clarity of the output, especially if you have a long simulation. Does not look as nice as 100 nanosecond. The output plot will show the RMDS relative to the structure percent in the minimized equilibrated system. If we wish to calculate RMD relative to... If we wish... Four. Again choose backbone. That's interesting. You're pressing forward each prompt one after each other. Friends don't let friends use Brenson. I don't get it. I don't get it. Mm-hmm. Okay, so I understood that I have to plot the computed relative to the equilibrated starting structure. This shows that how much the protein drifts away from the starting equilibrated structure over time. What this new command does. Okay, I think I'll do this also. I guess it's time to plot. Mm-hmm. It's all correct. Let's run this bad boy. Oh yeah. Equilibrated crystal. I should save it as could you give plot graph. What? Downloads. Downloads! It's just how much protein structure deviates from the equilibrated starting structure. How much protein structure deviates from its equilibrated starting structure over time. Useful to see if protein has stabilized during the simulation. Time measures how much protein deviates from the original experimental PDB structure. How we understand? I mean, both are same, right? I think it's stable around here. I don't know. Mm, the RMSD cannot be used as metric to assess convergence of simulation or determine stability. Just need to get the new window. Uh, 17. Hey Siri, set a timer for 45 minutes. Stop doing that.
45 minutes. Counting down.
Mm, next, more analysis analyzing compactness R. Let's go. Radius of gyration. What the fuck is that? Think you can go. We can see the reasonably invariant Rg values that the protein does not undergo any substantial elongation or compaction relative to its starting structure, thus it remains in compact folded form over the course of 10 nanoseconds at 298 Kelvin. This results is not unexpected but illustrates an advanced capacity of GROMACS analysis that comes built in. As with the RMSD plot on the previous page, the data have not been smoothed over 500 picosecond running windows in XM Grace. Okay, whatever the fuck that is. Next up, calculate the radius of gyration. Run the command. When prompted to select a group, choose a group corresponding to protein, usually number 1 and 0 depending on the system. Okay. Okay. I got it. No. We must be clear that when it comes to atoms, language can be used only as in poetry. That's pretty. So it doesn't need an select a number manually. The library file has been created. Plot in the pie chart similar to. Could you give me as the whole thing pie chart also guyrate.py. Can I just copy? No. Oh. We can see from reasonably invariant RG values that the protein does not undergo any substantial elongation or compaction relative to its starting structure. Okay. Okay, this means it did not have a big big change. Secondary structure. Protein structure is often as assist. That is persistence of alpha helices, beta sheets, etc. The GROMACS program, GMX DSSP, invokes the dictionary of secondary structures of protein, DSSP. Algorithm to assign secondary structure to each residue in the protein. To run this analysis, execute the following command. This is my next step according to the tutorial. I just can just run this command, right? Did I see something? Did I see a thank you? We must clear reading file. Read and cite the following reference. Journal of Chemical Information and Modeling. Modeling. Plot the DSSP result in pie chart. Also give just came off. Uh, there's a lot of things here. It's just helix, beta sheets, turn, coil. We have loops, helices. Helix, beta sheet, turn, coil. I don't even know these. Helix, beta sheet, turn, coil. Okay. Could you explain? Did I just save this? I did save it, okay. So did I run this 2 times? Oh, it's saved. Okay. Represent secondary structure content of your protein over time. Here's a breakdown, x-axis. This shows the simulation time. Y-axis, this indicates how much of a protein is in each type of secondary structure at the moment in your simulation. How much of a protein is in each type of secondary structure at helix show how many residues are in any kind of helix. If the line is flat, the helix content is stable. If it dips, some helices are unfolding. Sheet represents beta strands, beta bridges. Changes indication formation of disruption of beta structure. Coil turns represents loops, turns, bends. Increase when helices or sheets unfold. So I would say these kinds of stood stable. Beware in bugs in the above code. I have only proved it correct, not tried it. You know, I do not even do that. Where's Chrome? Bro, just... No, just... Oh, yeah, that's good. Huh. Hydrogen bonds. GROMACS uses two criteria to determine if a hydrogen bond exists between two groups. I mean, if I understand, I just run this code. That's all I knew. I gotta select. I believe you have to select related to which search environment select main chain H plus. Oh, there's something called that. Main chain plus H, okay. When prompted in GROMACS, the main chain group includes 4 atoms plus the amide H atom, which requires for assignment of hydrogen bonds. Sieben. I think I should go for that. Selection has 259 acceptors and 127 donors. 646 atoms. Numbers have life. They're not just symbols on paper. Shakuntala Devi. I do remember that woman back in school. Group 8 for both selections. Of course, I'm gonna do that. Sidechain has 119 acceptors, 83 donors. Checking for overlap in atoms between sidechain 1314 atoms and sidechain 1314 atoms. Okay, a little. Finally, we compute hydrogen bond between protein and water. Okay. Protein 12. I'm gonna go 113. Protein. 13 is salt and 12 is water. Let's go 13. Plotted together, results should be resemble what's shown here. Okay. Run that shit. That graph is so different. Oh, it's right. Main chain. Okay. Could you explain? Hydrogen bond analysis of a protein system during the molecular dynamics simulation. X-axis time in nanosecond, which shows the progression of your simulation over time, even though your trajectory frames were stored in picoseconds. Blue line, May hydrogen chain, hydrogen bond within the protein backbone, including amide hydrogen, the blue one. Oh, wait, I need to read the real deal. Did you save it? Yeah. Oh, yeah, I did save it. The blue one, main chain. Orange, side chain hydrogen bond. Side chain hydrogen bond. Hydrogen bonds among the side chain of amino acids. These can stabilize tertiary structures and contribute to the protein folding and interactions. Okay, green line. Protein, water, hydrogen bonds. Hydrogen bond between the protein and surrounding water molecules. This reflects solvation and protein water interactions, which are important for protein stability and dynamics. Green line. So that is the highest number of hydrogen bonds. So how do you proceed after this? In each case, the number of hydrogen bonds is relatively consistent over time, which is to be expected in the case of short simulation like this. Lysosome forms a large number of hydrogen bonds with water, roughly 55 within the backbone, and fewer among side chains. Did we just complete the whole lysosome in water simulation? Oh, no, my headphones. No way. It took me 1 week. I mean, one hour a day. You have conducted a molecular dynamics simulation with GROMACS and analyzed some of the results. This tutorial should not be viewed as comprehensive. There are many more types of simulations that one can conduct with GROMACS: free energy calculations, non-equilibrium molecular dynamics, and normal modes analysis, just to name a few. You should also review the literature and GROMACS manual for adjustments to the MDP files provided here for efficiency and accuracy purposes. If you have suggestions in improving this tutorial, if you notice a mistake, if anything is otherwise unclear, please feel free to email us. We know that it's not an invitation. This is not an invitation to email me for GROMACS problems. I do not advertise myself as a private tutor. Yo! Clone Open Commander, not gonna lie, you are on time. I just completed the GROMACS simulation. And this is not an invitation to email me for GROMACS problems. I do not advertise myself as a private tutor or personal help service. This is what GROMACS user form is for. I may help you there, but only in context of providing service to the community as a whole, not just the end user. I appreciate, I respect that. Virginia Tech. Is it bad if I ask you, is this you? Oh, protein gyration. A lot of files. Clone open commander. Do any professors at your school do simulations? I actually don't know. I mean, right now I don't think so, but next month, when my classes start, I'm gonna the first one of the first classes I have is on bioinformatics, and the classes I'm gonna choose was sequence analysis, biological sequence analysis, machine learning, introductions to AI. I give my most preference to sequence analysis, and I'm sure those professors would be doing any sort of simulations. I really want to know about those. And I do plan on contacting them before I head to the university. But do you, I think the professors at bioinformatics section should be doing good idea. Yeah, because I want to know what are they doing. And yeah, this is done. Whoa. Looks like I just did my first GROMACS simulation. Exactly, congratulations, it's a huge milestone. Preparing the system, running energy minimization. There's more to this, okay. If you want, we can make a quick roadmap of all the analysis you have done and what comes next, so you have a clear picture of your workflow and results. Uh, I mean, okay, so yep, my PhD dissertation was on MD simulations of protein bound to a specific lipid. Okay. Well, if you don't mind me asking, I did this like with the use of ChatGPT. So, uh, what do you think? Do you think it I could learn more from this, or it's like I have a long way to go before I do something like this? Cause I don't. I should say I did understand maybe 70% of what I did, or maybe 50. The rest I just don't know. You just learn how to run it. The issue is parameterizing the system usually. Okay. So parameterizing, you mean no, like understanding how the code works, or making new parameters, or understanding the parameters on how these work. I just started coding, so I still don't know how this works, and I have a long way to go. So, could you explain what I just did? So usually The molecules that you want to study don't have parameters. You have to calculate them. Oh, and then introduce them into the MD. I forgot. Molecular dynamics software. Parameterizing is just knowing the constants for the potential energy. Look at the potential energy terms and you'll see what I mean. Okay. Okay, I should say I did understand what you said now. Mm-hmm. So this for what I did, it's like I just simulated from using data of the lysome protein that other someone else made or someone else calculated and yeah made the file for it. Okay. Mm-hmm. So if I want to do any sort of simulation on something that is not part of that is still not uh, in the MD software, then I have to okay. I did understand. Take the lysine protein, prepare it in a simulation, put the protein in a realistic environment, adding ions, neutralize the system charge, and mimic physiological conditions. Physiological conditions, okay. Relax the structure to remove bad contacts and steric clashes. Stabilize the temperature while keeping volume constant. Stabilize both temperature and pressure. Simulate realistic protein dynamics over time. Correct for artifacts from periodic boundary conditions. Analysis. Radius of gyration, secondary structure, hydrogen bonds, temperature, pressure, density. Mm-hmm. Mm-hmm. Potential energy is the energy stored due to the interactive between atoms. It is calculated from the force field, which defines how atoms interact through bonds, angles, torsions, and non bonded interactions. The total potential energy is essentially E bonded plus E non bonded. These involve atoms directly connected to covalent bonds. Covalent bonds, bond stretching energy due to deviations from non bonded terms. These involve atoms that are not directly bonded. Optional corrections. Some simulations include dispersion corrections, corrects for trunications of van der Waals interactions. What do you saw in the EM step? The EM process minimized EPOD. Negative potential energy indicates a solid, stable structure, more favorable interactions. F max tells you the largest force acting on an atom. If it's too high, your system may have clashes. Okay. Could you explain I never parameterized Type. Oh, dude. My wording, especially some of the English words, I fucking hate it. I never parameterized by own molecule besides the column part. My own, okay. Force field development is like the hardest thing in molecular dynamics. Force field development. What your system is simulated light and water. This means your potential energy comes from all interaction within the protein, within water, between protein, water, and ions. Components of potential energy in your lysosome simulation: bonded interactions, angle bending, dihedral torsions, improper torsions. Key idea: these terms keep the protein chemically correct as it moves. Okay. Non bonded interactions. Clonopin Commander, do you think what I did could go into my GitHub repository? Like, can I put these, what I did, into GitHub? Do you think it's possible? Like, do you think it's valid to put it? And I don't know anything about GitHub, so I might just said a really stupid thing, but it's just a doubt. Force fields are backbone of molecular dynamics simulations. Without them, molecular dynamics would have no rules. A set of mathematical functions and parameters that describe how atoms interact. It defines bond interaction. Think of it as rules of physics for your atoms. Bonded terms. Oh, these maintain molecular geometry. Bond stretching energy when bond is longer or shorter than its equilibrium length. Dihedrals. Non-bonded terms. Force fields are carefully tuned to reproduce both experimental observables, quantum mechanical data, steps in FF development. Select a chemical model. Parameter. God damn it. Parameterize. Bonded terms: set bond lengths, angles, dihedrals. Parameterized. Paramet. I know I can say the word parameter. Parameter. Parameterize. I don't think it's worth putting it on GitHub. Usually only code goes there as a repository for future use. Okay, so these. Okay, this is not related to GitHub. Okay. I think the title is kind of wrong. Wrong, because this does not belong to coding. Is this coding what I did? I don't think so. Or is it? Also, okay, GitHub usually. No, not really. I knew it. So the title is kind of fake. Okay, so I should say something like beginner MD simulation journey, stuff like those. Select a chemical model. Sure. Force fields in your lysome simulation. You used OPLSAA. All atom. So, Clonopin Commander, how would you recommend I move forward? Like, should I look into more simulations or should I go deeper into these? What are I for me it looks like there's a lot of ways I could move forward. It looks like a branch or route. It looks like route. I can go any direction. Oh, okay. You know what? Yeah, that's actually a good idea. I could say that I did try using GROMAC. You want to save your academic energy points for what matters. Yeah, that sentence is so true, but it's so sad when I heard it. It's like I do have a limit for energy points, but there's a lot of time. So what I would be a beginner's Oh, I really want to see my. What are these chimera files? Oh shit, chimera is loading. It's still loading. 0 KB received? I mean, it's the same thing, right? It's the same thing. And is that two arrows? What the? What happened? Arrows are beta sheets. Oh, they did have meaning. Okay. So, oh, okay. I did not know that. I thought it was like energy flow or something like, okay, beta sheets. So, if I understand, this is the protein that's seen inside eggs, right? Yeah. What's this? Is it the same thing? Oh no. EMGRO. Oh, okay. Containing one model, 3,876 atoms. Okay. What else do we got? Solving ions. Looks the same. NVT grow. Different colors. I'm a big fan of colors, I guess. NPT grow. We should probably learn how to read NMR spectra since you have a test on it. You are right. I guess I should stop on that. And close this. And that is finally done. Oh, a lot of codes for Python. Oh, what did I just delete that? No. Well, peace out, YouTube. I'm gonna end the biocoding stream because that it's almost 1 hour and I gotta look into the chemistry. So I'll be continuing that. Peace out, YouTube.